Hey there, guys. My name is Ryan Schul. Welcome to my data science channel. So, in the project today, I want to take you through the ins and outs of supply chain management, and we're going to look at an example of supply chain bottleneck, where you get into a spot where the supplies, the raw materials, whatever you're shipping, just can't go, and there's some issues, and you have to try to manage that efficiently and effectively, and actually try to predict what kind of issues could disrupt your supply chain, right? So you want to minimize the risk of disruption and have a smooth operation. That's the whole point here. So why does interpretability of a model matter? We're going to look at a couple examples of doing the modeling and then how to interpret the results of the model. It's actually very important because this enables us to debug and improve the model to help it make accurate predictions. And if it's not, very accurate, we can tune the model, we can add hyperparameters and things like this to improve the performance, or we could just test a different model, right? There's about probably 44 or 45 regressors at this point and about the same number of classifiers, right? So if one model doesn't perform well, we can plug that one out and plug in a different model, or again, apply hyperparameter tuning or performance improvements tweaks to help the model to make better predictions. So bottlenecks are disruptions in supply chain, and they can come from overall inefficiency in the system. Common causes are shipping shortages, container scarcity, port congestion, things like this, right? Labor shortages, factory workers, drivers, warehouse staff boycotting the job, right, or walking out. Things like manufacturing delays, raw material issues, unavailability, quality materials. It could be poor quality, and they have to destroy the batch and remanufacture. All kinds of things could disrupt the system, including external shocks, right? Things that we can't even really control. We can try to anticipate it and try to work it into the model and try to, make predictions into the future based on external shocks. But these are more like strikes, tariffs, geopolitical conflicts that we really can't control, right? This is beyond our control. So let me import the data here and show you how this works. Control Enter to run. Okay, and the source of the data comes from over here. I give you the source right here. So if you're looking for this data, it comes from there. You can copy and paste that link into your browser and download the CSV file, and you'll have everything you need. So this is what the data looks like. We have product type, SKU, what is this? Availability, number of products sold, revenue generated, customer demographics, stock level, lead time, order quantities, shipping times, so on and so forth, shipping carriers, shipper, supplier name, location, and what else we got over here? Production volume, manufacturing lead time, manufacturing costs, routes, and overall costs. Okay, so pretty basic. I can go ahead and do some EDA. This is exploratory data analysis. This is looking at different carrier A, B, and C. So believe it or not, this is what the shipping characters are called. You think they would have something that's a little bit more definitive, some name that actually describes who this is, but this is how the data comes to us. So we're just using what we have. So shipping carriers and shipping times, right? So the y-axis is measuring the shipping time, like how long it takes to move the raw materials around. That's the shipping time, and then this shipping carrier comes from here, right? And we're looking at box plots, so we can see the longest shipping time here for carrier B is 9, a max of 9. That could be days, it could be weeks, it doesn't specify. The minimum is 1. I'm guessing it's probably weeks. We have the Q1 and Q3. So Q1 is 3.25. So about 1/4 of the material shipped come in 3.25, let's say, weeks. Let's say this is international shipping, 3.25 weeks. Sometimes in Q3, it can go up to 7, and the max again is 9. So these box plots are really nice. It shows you the distribution of the data and given the highs and the lows too, right? So again, the high over here is about, it's kind of hard to read. I think that's a 10 that I see, and the low would be 1. This one's a little bit easier. This is 10. I can see that. And the median is 7, and minimum is the 1. Okay, or the minimum is 1. So supplier name, again, very generic supplier, 1, 2, 3, 4, 5. We're looking at average cost by supplier, and the plot comes from here. We're getting the average cost, putting that into the box plot or into the bar plot. The first one is a box plot, right? This is a plotly box and a plotly bar. So in the first case, we're just using a raw data frame. This is DF for data frame. It comes in with shipping carriers and shipping times natively. That's given to us. If we want to look at the group by supplier name and get the mean cost. We can use that for average costs, and then we have supplier name and costs built in there, right? So that's how we get the bar plot and the box plot. So let's look at the first model here. I'm going to hit Control Enter to run it, refresh it, and make sure everything is fresh and loaded into the system. So I'm going to look at the independent variables. Anything for the features, the X features are independent. This comes from df encoded. We have to encode all the variables because some of these variables are not numeric. Anything that's numeric can be fed into model just as is. So anything like availability, number of products sold, revenue, price, this cannot be fed into the model. We have to convert that. Okay, anything that's not numeric. So carrier B, supplier 3, Mumbai, these all have to be encoded either using a process called one-hot coding or label encoding, or what's the other one? Categorical encoding, right? So there's 3 ways to do the encoding. I have a video about that: one-hot coding, label encoding, and categorical encoding. So anything that is a number has to be encoded, and this is the dependent variable that we're testing to make predictions on. This is the overall cost to ship the materials. Okay, so we want to understand how much does it cost and what is overall bottom line expense to us if there's a bottleneck in the system and it causes our supply chain to to be interrupted or to be disrupted, whatever you want to call it. So I'm using a random forest regressor right here, training, testing model. Here's my model. I fit the model. And then based on that fit model, I'm just calling it model. It could be RF model, doesn't matter. Control F, I'll show you where this goes. So we train, test the model over here, fit it, and then call the model, dot feature importance. Okay, we want to look at which features have the most significant influence on the dependent variable. So which of these independent variables above over here have the highest statistical influence on the dependent variable? Again, the dependent is cost, and the dependent is cost, and the independent is everything else. Okay, so when I look at this, I can't tell like what is driving the cost. Is it route? Is it product type? Number of products sold? Lead time? Manufacturing cost? So on and so forth. I can't tell, right? But the model is going to tell us. So we look at the feature importance. We're trying to predict the statistical influence on the target variable. Order quantities actually has an influence on the cost 14% of the time. The next biggest feature importance item here is lead time. The third would be shipping costs, production volumes, and manufacturing costs. And these have the least impact on the cost of the product. So product type, inspection results, shipping carrier, route, and supplier name. So yeah, it doesn't make sense that the supplier name would affect the cost to ship the product. I think I can figure that one out. But the route actually doesn't have much influence either. I did not know that. And the shipping carrier doesn't have much influence either. So you know that these are pretty I guess negotiated prices. Like all these carriers have very similar costs. Otherwise, if the cost of the shipper influence the cost of the product being delivered, this would be at the top of the chart here, right? So all these costs for all the shippers that we're using, what did we say? There was 3, I think, or 3 carriers. So shipper is different, I guess. But what's the shipper over here? Let me look at it. Shipping carrier, A, B, and C, right? So A, B, and C, they have pretty similar costs, right? This is the shipping time. It doesn't show us the cost over here. That's fine though. Average cost by supplier, these are all pretty similar too. Okay, so the cost is not a big factor on the total cost for this for a supply chain network. So now we have some information. We can start to make some very intelligent decisions, right? But we want to look at the model and have the model explain to us what's happening, right? So we're going to learn from the model what's going on here, because I can tell you from experience, the random forest model is really a black box. If you look here, we're using random forest regressor, again, to try to predict the cost for this supply chain network to ship the items, right? So when everything goes to this random forest regressor, what this model is doing is taking every possible combination of every feature, slicing and dicing it every possible way, and looking at the outcome of the influence on the target variable, which is the cost, right? So it could be the first 2 columns, the first and the third, the first and the fourth, the first and the fifth, and it goes through all those columns, and then the first, second, third, right? Second, third, fourth, fifth, sixth, things like this, right? So it takes, and then 1, 2, 3, 4, and 1, 2, 3, 4, 5. So you look at every combination and see which combination of those features are having an influence on the cost, right? But to break apart that model and understand under the hood what's really going on is actually kind of complicated. There's a few things you look at called Gini impurity and entropy, and is the impurity decreasing or increasing? If it's decreasing, the model is learning better. If it's increasing, the model isn't learning quite as well, right? So you can have a couple of parts of the model that you can sort of like pull apart and analyze. But overall, it's very hard to tell what the random forest model is doing, right? So we want to take a different approach and look at two methodologies to help us determine what's really going on with this model, right? So we're going to look at SHAP and LIME. Basically, SHAP stands for Shapely Additive Explanations, and SHAP draws on cooperative game theory to assign important values to each feature. So like we saw before, this is feature importance. How important is this feature to predict price? This has 14% influence on price, right? The lead time here has an 8.5% influence on price, and this has about 6.9, almost 7% influence on price. So we can see that, right, for the feature importance. That's kind of how SHAP works too. It's looking at the important features to drive the target variable, right? And what has a statistical impact on that target. So it's like determining each player's share of team success. This is using a concept called game theory. And SHAP provides basically a global overall model behavior and then local or individual predictions based on insights, making it very versatile, right? So we have the overall model behavior and then the individual predictions for each feature in the model. Okay, so an example would be a credit scoring model. SHAP might reveal that a customer's income contributes 40% to the credit score, but the credit history accounts for another 30%, right? So this kind of insight or clarity can help loan officials understand and explain and make accurate decisions about which customers to do business with, right? You don't want to do business with somebody that's going to apply for a credit card, take your money, and then never pay off the amounts of the card, right? You want to make sure that the person is going to repay. If you know 40% is based on the person's credit score and 30% is based on credit history, now you're 70% close to understanding what is driving that target variable, right? So that's how these things work. The strength is consistent and mathematical rigor based on Shapley values from game theory. It's model agnostic, right? So it works in any model in the machine learning universe, and it offers rich visualization like summary plots and force plots into intuitive understanding plotting system, right? So we'll see like a vertical plot in the layout and then a horizontal plot in the layout of that. Okay, so I'm going to go ahead and run the model, Control Enter. We have the XGB regressor now. So this is XGBoost, a little bit similar to the Random Forest regressor that we saw before. The difference is this is a boosting model. That's why it's XGBB or XGB booster. The other Random Forest is an ensemble, what's it called? Booster, a bagging model. That's a bagger. So you would take everything and run it in parallel. That's how the Random Forest works. Everything is done at the same time. With a booster, you try one model and then take the best results from that, move it into the next model, take the best results from that, move it to the next model, and so on and so forth. So in both cases, you would run through a bunch of models. That's why they're ensemble. But one boosts everything up to another level. That's the XGB. And one bags everything together at the same time. So we have the model here. We fit the model. And the model is going into Shapley Explainer. And we can see here the lead times, locations, shipping costs, routes, and prices. All of this contributes, again, to the ultimate cost of making the shipment. Okay, so you can see the vertical layout, the lead times, location, shipping costs have the highest influence. The lowest influence is supplier name, manufacturing costs, and inspection results, right? So down here you see the name, right? Inspection results and product type. And you see inspection results, manufacturing costs, and supplier name. So where's supplier name over here? I don't see it. Oh, here. So it's toward the bottom. And like I said before, like, well, why would the supplier name influence the cost of the product? Really, it doesn't, right? Unless maybe you're dealing with a big brand product like Prada or Louis V or something like that. But that would be more like the manufacturing name. Like the supplier name really doesn't really matter unless Louis V does supplying too, and you're paying a premium for that. So the name of the shipper, the supplier, doesn't add anything to the cost over and above what other shippers would add. So basically the horizontal axis impacts the model's output. The further you are from 0, the greater the impact, right? And there's a left and the right side too. So on the right side, you'll see more reds. This feature increases the predicted cost. And on the left side, you see more blues. These features lower the predicted cost. So everything on the left-hand side of this axis, it splits this on in the middle, is going to lower the cost, right? That's the target variable that we set over here, okay? And everything to the right of this line that splits everything in half is driving up the costs on this side, okay? So that's how you interpret the model. Again, blues have lower feature values, reds have higher feature values. The lead time is a top feature. The blue is a low feature, and the red has high feature value, okay? The lead time is a top feature. Blue dots have short lead times, and red dots have longer lead times. So this is more neutral or slightly positive. This can have a negative SHAP value. So again, the blues on the left are going to pull everything to the left. On the right, it pulls everything higher to the right? So lead time, location, shipping costs are the top three. We see that lead time, location, shipping costs. Some low values, blues, reduce the cost, while other red values increase the cost. Shipping costs, higher shipping costs, reds generally push the prediction up. Right, and lower shipping costs hold the whole thing down. The costs are lowered, right? To round out the top ones over here, roots, price, and order quantities. I think that's it. Roots, price, and defect rates actually comes before order quantities, but they're pretty close. Probably substitute one for the other. So again, some roots likely encoded as red values are going to be more expensive. The blue values are going to be less expensive. Higher prices are going to be red, sometimes increasing overall predicted costs, like what else? Shipping routes. If you take a longer route, it's going to cost more. You burn more fuel. If you pay more for the fuel, that's going to drive up your cost too. Okay. And then order quantities. Higher quantities usually increase costs, right? If you order a couple items, that's probably not going to cost too much to ship. If you order a couple thousand items, that's guaranteed to drive up the cost of shipping, right? So pretty intuitive. Now, let me see. This line, I guess actually, I'm looking at this right now. I think this actually goes in the next section. So let me cut that out. Oh, that goes there. This goes here. Okay. Okay. I put that in the wrong spot. Let me fix that up. I don't need this. Okay, so we got the first part of SHAP done. Now we're looking at SHAP waterfall. So this would actually look kind of like a cascading waterfall, believe it or not. So we have the top value, 529.24. You can see this at the bottom. This is E of f of x. F is a function of x, and E is just the variable that we're using here. So 529.46, this is a baseline prediction. This is the model's average output across all training data. So the average cost for everything in the whole like system here is $529. As I say, what the unit is probably per ton or something like that. I'm not sure exactly because the data doesn't specify. But let's assume 529, about $530 per ton to ship the product. The f of x is at the top. It's 187.52. This is the final prediction for this particular observation. Okay, so again, we have the local predictions right here, and we have the global predictions. So the global would be 529 or 530. We can just round it. And then for each of these individual items here, these different features, it's about 187.75. That's what it is. Okay. So the plot shows how each feature pushes the prediction from the baseline to the final value. So we have some things that pull up the feature 0.43, 21.78, driving up the cost. We have a lot of features here pulling down the overall cost. So we go from 529 that actually revenue generated is offsetting some of the costs. Shipping costs is offsetting some of the costs. Maybe they're what would that be, like you have a network that you work with or a partner that you work with, maybe that offsets the cost. Customer demographics is dragging down the cost. If I see this route is increasing cost, availability is decreasing, price, location, defect rate, and lead time is decreasing a lot. So we go from 529 to 187 when you look at all these individual contributing features here. So basically, the lead time drags down the cost a lot, pretty substantially, like 126 over 529, almost about maybe 20%. So essentially, this is telling me if you have enough lead time in your order, you can pre-order everything you want and save yourself from paying a higher premium at the end. And then you have to pay a lot more because you're in desperate need of these products and your warehouse is running so low on these supplies, right? So if you plan ahead a couple of months, maybe 3 or 4 months, and you can build up the inventory in the warehouse, you could save $126. Again, this is making an assumption per ton because you anticipate the need for these products being sold. So that's another part of the business. We're looking at supply chain. But if you work with forecasting or pricing or something like this, and these guys collaborate with your team because you're on the supply chain team, they can say, okay, we can forecast this revenue, we can forecast these prices, we can adjust the prices and move more inventory. Then the supply chain guy has to say, okay, I can get 4 months worth of inventory. I have to put in an order quick though. I have to get it now, and it's going to save me $126 per ton. Okay. So this model right here, the SHAP model, is really breaking apart the random forest model and showing us how all these influences contribute ultimately to the cost of the product, right? When I look at this, I don't get any kind of story like that. I don't have any background, any insight. When I look at random forest, okay, it's telling me feature importance. That's very useful. That's helpful. But SHAP is really exposing what this model is doing, right? Because it's showing you all the details, all the features from a global perspective and from a local perspective, right? These are all the local features that feed into that model comprehensively, right? Um, so that's it. And then we have the values over here. Okay, we just discussed that. There's 2 positive values, right? Pulling up the cost, but most of these are negative and they're actually pulling down the cost. So it's saving you a lot of money. So despite all the downward pull, Route 1 slightly pushed the cost up, and a few other negligible features added up to less than $1 per ton, right? So that's what we're looking at. The model predicts low cost 187.75 because this product has a short lead time, low defect rate, and is cost efficient. Now, let me see. I think that changed 187.75. Again, making the assumption dollars per metric ton shipped. That's the assumption here. It doesn't specify in the data. That's a reasonable expectation. And location has a reasonable price, and availability has also an impact on the total cost to do the shipping. So that's one model. So we have the SHAP model. We just explored that. Another model is somewhat similar, slightly different. It's called LIME. This is local interpretable model agnostic explanation. So like the first one, Shapley is model agnostic, LIME is model agnostic. Doesn't matter which model you feed into it, it can handle it, right? It can handle the input. Like what's agnostic mean? It doesn't matter what is underlying. Email could be agnostic to a PC or to a mobile phone or to a Mac. So it doesn't matter if you log into your email on a Mac, on a phone, or on a PC, you can access your email. It's agnostic to the tool that you're using or the device that you're using. Okay. So Lime takes a different approach, somewhat similar, but kind of different, focuses on individual predictions by approximating the complexity of the model, okay, and making interpretations like a linear model in the vicinity of the prediction. It's like zooming in on a single decision to see what tipped the scales in your favor or in your disfavor, okay? So for a neural network predicting sentiment of customer reviews, sorry, I have to get my ice water or my throat is going to explode. I don't know why I have all these throat irritations constantly. It's very hard to talk, but it is what it is, right? So to understand what a neural network is doing is extremely complicated. That's even more complex, more of a black box than the random forest model, right? So you really need a model like SHAP or LIME to expose what the model is really doing, because it's a black box. You don't know. You have your inputs, you have your outputs. You have no idea what's going on in between all the neural network connections, okay? A little bit like the human brain. Like you have inputs through your eyes, through your ears, through your nose, touching, feeling, tasting. Those are your 5 senses, right? And your mind is processing all that information, and then you can have some type of output. Like you could taste ice cream, right? Your mind is making a determination, and your brain can form a coherent thought, and then your mouth speaks. This is delicious ice cream. This vanilla with Reese's peanut butter cups mixed in is delicious, right? Like what's going on in your brain to form the tasting and the sensations in your mouth, and then come out with a final report on that ice cream. There's a lot of stuff going on, but it's very hard to understand and interpret all the nuances of that, right? It's a black box. The human brain is a black box, and these models are the same. You can't understand what the model is doing. You take the output, and if it looks reasonable, you accept it. If not, then you test a different model, right, and get away from the black boxes. But you have to have a lot of confidence that this is doing what you expect it to do. But the upshot here is that the line model and that the SHAP model will help us expose the inner workings of that and understand what the model is doing on a more granular level. So model agnostic, ideal for explaining individual predictions such as fraud detection or text classification. Okay, also great for easy implementation interpreting, especially for simpler models. For more complex models, it will handle it as well. But simpler models are just going to be easier to understand and to explain to your customer base. The limitations can be unstable due to random sampling during perturbation. This is like the ingestion of the data and the model doing all its work. And it's less effective for highly complex models where local approximations may oversimplify what the model is actually doing. Okay, so let me go ahead and run it, Control Enter. So the X comes from the original variable that I set over here. So remember, with SHAP, we're feeding in the model, we're testing the model over here. This is XGBoost. The X comes from the F encoded. So we're taking that X variable. This is all the independent variables. Remember, the original X variable comes from here. Okay, we're encoding all the features. Features goes down here, right? So this is flow. You have to look at the flow here. This is XOR features. I'm calling it features. This is almost the same thing. This is target. So now, again, we're using the features or the X. You can call it whatever you want. Typically, the naming convention is X. We set the X over here. Look at the I location. This is the index location of I. And we're looping through all the different rows of features, or not rows, different columns of features, right? So we're making a prediction based on each one. We see the predicted value over here is 187.75. And 90.61 is the max. So the minimum is 147.13. The average, or the most likely, I think, is 187.75, and the max is 960. Again, the assumption is this is dollars per metric ton to do shipping. We're trying to predict the cost, right? So the line is telling us the summary of the top left box, 581.59 is the predicted cost. So where's the 581? Let me look over here. I think it's changed a little bit when I ran it. So I'm going to put 960. This is the max, really, 960. And the min is 147. 147. And the most likely is 187. Okay, so I fed in some more data before I tested it. So these numbers come out a little bit different. 187 is the cost. The minimum 147, and the maximum cost per metric ton is 960. The orange bars show how close the predicted value is to the upper bound. Okay, so again, kind of like the SHAP, the positive is on the right side, negative is on the left. And with the SHAP, you have the right, or the red was on the right rather, and then the blue was on the left. Now we have orange on the right and blue on the left. So kind of similar, a little bit different. On the left panel, you see features sorted by their influence on the prediction variable, right? So we have some negative influences. Location and defect rates are pulling down the cost. Routes and order quantities and customer customer demographics or something. I'm not sure. That's getting cut off. Oh, demographics. I see it over here. Customer demographics are driving up the cost. Shipping costs and availability of products is driving down the cost, especially results in lead times is driving up, or lead times greater than 25. That makes sense. 25 days, or this could be weeks. I'm not sure. We don't have the units. Greater lead times are driving up the cost. Lower lead times are saving money, right? So it's pretty intuitive. This is pretty nice how this works out. So the largest driver of predicted cost is large order quantity, right? Do we have order quantity? And we see that here. So I'm going to get rid of this 0.96 because I was doing a different experiment before, but it's the same concept, right? High lead time and manufacturing lead time also push up the cost. Do I have that 29? I don't, so I'm going to get rid of the numbers just to make this more generic. Probably talking about days there. However, short lead times for the delivery and low shipped cost help reduce it, right? So that makes sense. That's pretty intuitive. This is saying low defect rates and reasonable shipping time also suppresses costs. That makes sense, right? Totally makes sense. This is totally intuitive. Now, on the net, the upward factors outweigh the downward factors, landing the prediction at net 187. Okay, so I'm going to put that over here. Running a different process before, so the numbers are all different, but the concept is exactly the same. Okay, so now I want to look at the SHAP values. Again, using X columns, these are all the columns of the independent features. Remember, the independent features was everything that we used to predict the cost. And we're looking at SHAP values greater than 1, anything that has a very low influence on the target variable. I'm not too interested in that, but anything that has like at least 10% or greater, that could impact the target variable. Let's look at it. If it has a 1% influence on the target, I don't really care. You could look at it. It's probably a waste of time. That would be considered de minimis or of minimum usefulness, right? So we don't really need to get too concerned about that. So anything greater than 10%, we're going to go ahead and do one hot encoding for that, right? Yes, so we have the product type, price, availability, and so on and so forth to convert everything to numeric. Now I can use a plotly plot to go ahead and look at the intensity of the bottlenecks that can cause a disruption in the supply chain, right? So now we have the bottleneck flags. That's everything over here. These are all the flags. Again, taking binary values to say, is this going to have an influence on the cost of shipping, and try to anticipate what these bottlenecks are going to be and then manage that expectation accordingly, okay? So we see product type has some influence, price, availability, but this kind of scattered all over the place and it's kind of just a mess. So any good chart should answer questions and not generate questions for you. So when I look at this, I'm kind of saying, okay, bottleneck or not bottleneck, everything is binary. We don't need these things in between 0.8, 0.6, 0.4, or 0.2. It's a binary outcome. It's a bottleneck or it's not a bottleneck, okay? So there are a lot of bottlenecks here, but where they mostly concentrated, it's kind of hard to determine that. So I would say this heat map is not super useful, but it's good. It's a good first start. But let's see if we can get this into a state where it's just more useful, right? Let's look at the top features here. So we're going to sort everything in descending, sort values based on bottlenecks flags in descending fashion, right? So ascending equals false is the same as descending. I don't even think they have descending in this case. It's either ascending true, so we're going from high numbers up to low at the top. Descending, the high numbers are at the top, and then you go down to low numbers at the bottom. So ascending equals false is the same as descending. We're getting the top 10, and we're going to run the same heat map. Control Enter to run it, and the subset df, if you look close, it comes from here, right? Originally, we used bottleneck flags. So if I Control F that, you can see the highlight. Bottleneck flags come from here. That's what we produced from that one hot encoding exercise. Now we're looking at the top 10 bottlenecks. Now this is a lot more useful. So we can see product type actually has some influence on the cost to do the shipping, right? So anything that's light over here, anything that's kind of like a tan color, I'm not super interested in. It just means no bottleneck. We don't have to get concerned about that. But any of these dark burgundy things that's colored like red wine, these are bottlenecks that we have to be aware of. So number of products sold, that could be a bottleneck. Availability. Again, this heat map just helps us to focus on what's very important here. Lead time, almost everything except for this is a bottleneck. And over here, shipping times, everything but 1 is a bottleneck, right? Over here, everything but 2, supplier name is a bottleneck. Although that looks kind of weird. Like I'm not sure how a supplier name can create a bottleneck for your supply chain distribution channels, but according to the model, there's some influence. I wouldn't say that's huge. The name of the shipper should not cause a bottleneck, but it must bleed into the target variable somehow. Okay, So moving on here, we're almost done. So basically, we took the top 10 bottleneck items or counts, right, and converted that into a chart that makes a little bit more sense than this. This is just too busy and it's too confusing. This is a lot more useful right here. The production volumes has a huge influence on bottlenecks, and manufacturing costs has a huge influence on bottlenecks. So production volume. So if you produce a lot and then you ship a lot, then you're probably not going to have bottlenecks. If you do production once a year, right, and then there's a stimulus for the product, but it's only made once a year, and you're already sold out and the warehouse is wiped out, then production volume is going to have an impact on the cost, right? So that makes sense. And what was the other one here? So everything has an impact on the bottleneck or creating a bottleneck. Manufacturing costs. So basically, if the manufacturing costs increase, that can affect bottlenecks too. Maybe it's more expensive to ship. It's harder to get the raw materials. It's hard to manufacture this thing. Once it's shipped, it's more unpredictable about the volume that's going to be sold or something like that. So we have to set up another meeting with the forecasting and pricing crew so we can understand that better. So this is just a basic histogram now, or bar plot of all of the counts of the bottlenecks. So inspection results, if there's a lot of inspection results, that's going to slow you down and it's going to take longer to ship from point A to point B. Order quantities, that has an impact, right? So these are all bottlenecks that we can use to predict what is going to impact the cost of shipping. Lead times, production volumes, routes, lead times. Again, I see the issue here. Lead time has no S over here, and in this case it has an S. That's a data quality issue. I'm not changing anything here, guys. Like if I was doing this for my boss, I would clean that up and drop the S or add an S onto the first. All I'm doing is reporting what was given to me. So that's a data quality issue coming from Kaggle. Supplier name. Now this one's interesting. I'm not sure how the name can impact the cost and create a bottleneck, but it is coming up as a pretty high count. 54 records are being counted here. So this does have some kind of influence. So to do a deeper dive, I would either myself or I would ask somebody to go and look into this. Like, why is the supplier name causing some kind of impact on the cost of shipping a product through the supply chain? So the way to do this pretty easy would be a cause and effect or causal inference kind of analysis to see what kind of cause the name has on the cost of shipping, right? There's always a cause and effect. If you have a cause and effect, that could be handled with a causation model, right? Or a causal inference model. So that one looks a little bit weird, but I'm sure there's a reason for that. The causation analysis would determine that shipping carriers, number of products, product type, customer demographics. So these have less influences on the bottleneck or creating the bottleneck and influencing the cost of the variable, the value. Shipping costs, again, over here, manufacturing lead times and transportation modes. So apparently this is shipping through boats or airplane or something that can have an impact. I'm guessing most of these long distance products are going on boat, and most of these boat costs for shipping are probably pretty efficient. Like they're pretty close. I'm guessing that there's not going to be a huge influence. Otherwise, transportation modes would be way higher on the left, and it would cause a lot more bottlenecks. I'm guessing they just put everything in containers, drop it on a big ship, and that's it. I don't think too many people are shipping by train or by airplane or boat. I think here everything is going by boat. Otherwise, transportation mode would have an impact, and it has almost none. Okay. So that's it. The final takeaway here: you can predict and explain supply chain bottlenecks using real-world indicators, shipping, labor, tariffs. You see the Trump tariffs are kicking in now, so inflation is already up like 2.5%, maybe 3% in the past couple of weeks. You can feel the impact right now in real time. Wealth and worker strikes, that can cause an impact on your shipping costs, right? Machine learning for forecasting is very useful for helping us to make these predictions and do these forecasts into the future accurately. Feature importance to identify key drivers and the cost of shipping, right? We saw that. That was the first model that I showed you, the Random Forest and the plot lead result. And causal tools to determine true levers of disruption. Again, like I would use a causal inference to try to determine why that supplier name is having a count of 54 times this is creating bottlenecks in our system and causing price um, to skyrocket up. So that is interesting. Can't totally explain that, but the point of this analysis was not to explain shipper name influence on cost. It was comprehensively to look at everything, everything in the universe. And I think we did that, guys. So that's it. 40 minutes. These things tend to go long. It always feels shorter. It feels like 15 or 20 to tell you the truth, but done a few of these videos recently and they all go over 40. Not sure why. But I want to tell the story, and I think the mission was accomplished. So I told the story of everything from supply chain bottlenecks and making predictions and counting, and then determining what has the influence on the overall shipping cost. So mission accomplished, guys. I'm going to wrap it up here. Thank you so much for your time. Hopefully this was informative and interesting and educational and even inspirational. Try to make it that way. So yeah, I'm going to wrap it up right here, and I will talk to you guys in the next video, which I'm going to drop pretty soon. Thanks. Goodbye.